Hi, in this video we are going to talk about array implementation of Deque. So we need to implement a data structure using array that supports these operations. Insert front, that inserts an item at the beginning of this data structure. Insert rear, that inserts an item at the end of this data structure. Delete front, that deletes the front item. Delete rear, that deletes the last item or rear item. Get front, that gives you the front item from Deque. Get rear, that gives you the rear or last item from the Deque. Size tells you how many items are there in the Deque. Is full tells you whether the Deque is full. Suppose you have a capacity in the array, and if size becomes equal to capacity, then you say it's full. Is empty tells you whether there are elements in the Deque or not. So here is pictorial representation of what we are expecting from this data structure. Suppose we create a Deque variable, right, of Deque did write. Now if we call insert front function, it should insert an element, and front and rear both should be pointing to this element or referring this element. Now if we call insert rear, then 20 will be added to this Deque and rear will now give you 20. And if we call insert front 30, then 30 should be added at the front of Deque, and now front should give you 30. So if I call get front, I should get 30, and if I call get rear, I should get 20 now. Now if you call insert rear, it should insert 50 at the end. Now if you call delete front, this 30 should be removed from the Deque, and now your new front should be 10. Now if you call delete rear, then 50 should be removed from the Deque, and this should be your new rear. At any moment, if you call size, it should give you how many elements are there in the Deque. Now please pause this video and think of an implementation that supports all these operations in big O of one time. Let us now talk about a simple implementation of Deque. In this implementation, we are going to maintain front always at 0 and rear always at size -1. So if we wish to add an item at the rear, suppose we wish to add an item after the size, we are simply going to do size ++, and we'll again get rear as size -. And if we wish to remove an item from the rear, we'll simply do size -. Now, when we want to add an item or remove an item from the front, we need to do extra work because we want to ensure that front is always at 0. So if you want to insert an item at the front, then you need to move existing items one position ahead, create a space for the front and insert the item there. And if you wish to delete an item from the front, then we need to move remaining size -1 items one position back and then delete this item and reduce the size. So in this simple implementation, insert rear and remove rear are simply big O of 1, but our delete front and insert front are going to be big O of n, where n is the size of your Deque. Now please pause this video and try to write down all the functions for the simple implementation, and then we will talk about efficient implementation where we have all the functions in big O of one time. In this simple implementation, we are going to follow this structure for Deque. So we do not need to maintain extra variables for front and rear because we can always get front at 0 index. We can get the rear at index size -1. So we are just maintaining size and capacity, right? We have a constructor where we initialize the capacity as C, size as 0, and we also create an array of the given capacity. Same as the implementation in Java. We have a class where we have size, capacity, and an array. We create an array of size, capacity with the constructor, and we initialize capacity as C and size as 0. In this implementation, we are not assuming that our Deque will grow dynamically when you have more elements than capacity. We have a simple implementation where Deque has a fixed initial capacity. We have discussed a structure of a Deque in C++ and class of Deque in Java. Let us now talk about implementations of different functions in the struct in C++ or class in Java. I have used one code here only because the syntax for these codes is almost same for C++ and Java. So in this simple approach, what we are doing, we have an array of given capacity and initially size is 0. When we insert at the rear, we simply go to ARR size and put the item at that size, right? And then do size plus plus. That's what we are doing at insert rear. Simply do ARR size equal to X and then do size plus plus. When we do insert front, we need to add an item here. So we need to move this 10 here. So in insert front, we are moving all the items, all the existing items, one position ahead. Array I plus 1 becomes equal to array I for all the size elements. So we create a space at the beginning and then we insert at the beginning. Insert rear again is simply going to have this element at size. Size is now 2. So we are going to have the element 30 at index 2, 0, 1, 2. And then we are going to do size plus plus. We do size plus plus in both the inserts and do size minus minus in both the deletes. Now we do insert 40. Again, to insert 40, we need to move these three items one position ahead. So that's the code which is going to move 20, 10, 30, one positions ahead, and then it's going to insert the new element at 0 index. We always insert at 0 index, front is always 0. Now delete front. Delete front needs to move these items one position before, and this 40 can be overwritten because we want to delete the front item. So what are we doing? We are running for I equal to 0, I smaller than size, and we are doing array I equal to array I plus 1. And then we are doing size minus minus. Now delete rear is simple. In delete rear function, we are simply doing size minus minus. That's all. In both the insert functions, we check for DQ is full. If DQ is full, then we cannot insert an item, we simply return. And in both the delete functions, we check whether DQ is empty or not. If DQ is empty, we cannot delete an item. So conditions for empty and full are simple. For full, we check size equal to capacity, and for empty, we check size equal to 0. Let's now talk about get rear and get front functions. So get rear returns the index of the rear item, and if the queue is empty and you are calling get rear, then it returns -1. Otherwise, index of the last item is simply always size -1 because we are maintaining the front item at 0. Get front works the same way. If queue is empty, if DQ is empty, then we return -1, otherwise front is always 0. So this is simple implementation of DQ data structure. The problem with this implementation is insert rear and delete rear, they are fast. They are both big O of 1 operations, but insert front and delete front, they are big O of n operations. Now please pause this video and think of an implementation where all these 4 operations are big O of 1. Let us now talk about efficient implementation. In this implementation, we are going to treat our array as circular buffer. So our insert and delete operations are going to work this way. When we delete from front, we are going to do front equal to front plus 1 modulo capacity, right? All the operations have to be under modulo capacity. When we insert an item at the rear, we are going to do rear equal to rear plus 1 modulo capacity. So when you have a DQ and you have a front and you have a rear, when you delete from front, you do front equal to front plus 1. And when you insert at the rear, you do rear equal to rear plus 1. And you do these under modulo capacity. Similarly, when you insert at the front, right, when you insert an item before the front, you are going to decrease the front. So you are going to do front equal to front -1 plus capacity modulo capacity. See, plus capacity we are doing to ensure that front does not become negative because front is an index. Similarly, when you are doing delete from the rear, delete from the end of the DQ, you need to decrease the rear. So what are we going to do? We are going to do rear equal to rear -1 plus capacity modulo capacity. So these are the things we are going to follow in this circular implementation. Now, let's take a look at the representation of DQ. This is Java representation, and here we have C++ representation. In these representations, we have array, which is normal that we used in the simple implementation also. We have capacity and size also that we had in the simple implementation. We are also having front in this implementation because this is circular array implementation and front is not always going to be 0. Front can be anywhere. We are not having a variable for the rear because we can always find rear as front plus size -1 modulo capacity, right? That's the simple way to find rear in your circular implementation. Let's now understand this implementation with this example. We have this array, we have capacity is 5, size is 0 and front is 0. Now when we say insert rear 10, we find out the rear using this equation. What is rear? Rear is front plus 0 plus 0 minus 1 modulo capacity. Now when you insert at the rear, what are you going to do? You are going to do rear equal to rear plus 1 modulo capacity. Currently rear is minus 1, you will make it 0 and your rear now becomes 0 and you are going to insert this item at rear. So that's how your insert rear works in this implementation. Let's now see insert front. So we want to insert an item before front. Front is currently 0, right? Initially it was 0 and insert rear function does not change front. Now when you want to insert at front, you need to decrease the front under modulo. So what you will do? You will make front equal to front minus 1 plus capacity, which is 0 minus 1 plus capacity, which is capacity minus 1. So your front reaches here. Front is now here. So let's mark these. This was rear earlier and this was also front. Both were 0. Now when we inserted 20, this is rear, but our front is going to be this much. Capacity minus 1. And you can notice that this still holds. What is front? Front is 4. And what is rear? 4 plus 2 minus 1. Right? 4 plus 2 is 6 minus 1, 5. Modulo capacity. Capacity is 5. So our rear is still 0. So we are matching with the equation that we have written here. Let's now see what happens when we insert 30. Insert front 30. So we are again going to do front equal to front minus 1 under modulo capacity. What is front right now? Front is 4. So we are going to make front equal to 3, right? And we are going to insert this item at the front. Now we do insert rear 40. So we are going to find out rear using front. What is front right now? Front is here. So what is going to be the rear? Rear is going to be front plus size minus 1. What is size right now? There are 3 elements, so size is 3. So our rear is going to be 3 plus 3 minus 1 modulo capacity, which is 0 only. Because capacity is 5 and 3 plus 3 minus 1 is 5. 5 modulo 5 is 0. So we get the rear here. We do rear plus plus when we insert at the rear. And now we insert an item at this index. Now delete rear. You want to delete an item from the rear. So to delete rear, you will simply do rear equal to rear minus 1 plus capacity, modulo capacity, and you will delete the item from rear, right? So you delete it and your rear now is here. Now delete front. To delete an item from the front, we will simply do front equal to front plus 1 modulo capacity. So our front was here, now front moves here and we deleted an item. And you can still notice front is here, rear is here. So front plus size minus 1 modulo capacity is rear. Still we have this expression being followed. Let us now talk about implementation of these 6 functions. So let's talk about this first function, get front, which is going to give you index of the front item. If Deque is empty, then it's going to return minus 1. Otherwise, it's going to return front. Please remember, in our structure or class, we have 3 members, front, size and capacity. And we are going to get rear as front plus size minus 1 modulo capacity. So our get rear function is, if Q is empty, then return minus 1, else return front plus size minus 1 capacity. So you can always get the rear item by using this index. Now let's talk about remaining 4 functions. If we want to do delete front, then we'll do front equal to front plus 1 modulo capacity and we do size minus minus. Before doing this, we check if Deque is empty. If Deque is empty, then we simply return. Let's now see insert rear. So rear we get using this function. So this function will give front plus size minus 1. And to insert an item, we need to add 1 to this rear. So I've done these 2 computations in one step. Front plus size is minus 1 plus 1 is front plus size. So we get the new rear as front plus size modulo capacity. And we are going to insert this item at new rear, right? So we do array plus new rear equal to x. And we do size plus plus. Let's now see insert front. Insert front means you need to decrease the front by 1. And instead of decreasing by 1, simply we are also adding capacity to ensure that it does not become negative. So we decrease it by 1 under modulo and then we put the item at the new front and we do size plus plus. Delete rear is super simple. Since we are not maintaining any rear variable, we can simply do size minus minus, because once you do size minus minus using this equation, you can again get the rear. Let's now see working of these functions with this example. So we have initially 4 capacity, size 0 and front 0. Now when we do insert front, we do front equal to front plus capacity minus 1 modulo capacity. This is what we do, right? And front is 0, so you are going to get the new front as 3, and you are going to insert this item at index 3, and you are going to do size plus plus. So you will have size equal to 1. Now let's do insert rear 20. So insert rear function is going to get the new rear as front plus size, right? So please remember, we are doing 2 operations here. We are getting the old rear, then we are doing plus 1 to it. Old rear is front plus size minus 1 capacity, and then plus 1 to it. So these 2 operations are done together. We get the new rear as front plus size modulo capacity. So what is our new rear? Our front is right now 3 and size is 1. So front plus size modulo 4 is 0. So we get the rear as 0. New rear as 0. And we insert this item at this new rear 20. Now we go to insert rear function again. And again we get the new rear as front plus size modulo capacity. What is front right now? 3. And what is size now? 2. 5 modulo 4. Capacity is 4 here. We will get 1. So we insert 30 here. Now we do delete front. When you do delete front, you remove the front item and you do front equal to front plus 1 modulo capacity. So right now front is 3, and if you add 1 to it, it will become 4. Modulo 4 is 0. So your front now becomes 0 and size is 2. Now when we do delete rear, we are simply going to do size minus minus. Size now becomes 1, and we are not going to change front. So we have talked about all 6 implement functions and their implementations, and we can notice that we have the time complexity for all these 6 functions as big O of 1.